Welcome to the first lecture on organometallic chemistry. The title of this course is Transition Metal Organometallic Chemistry from Principles to Applications. To begin with, let me give you a brief overview of organometallic chemistry. Organometallic chemistry lies at the interface of inorganic chemistry and organic chemistry and has implications both in the areas of organic as well as inorganic domains. One important aspect about these compounds are that they are very difficult to synthesize, very difficult to handle, as they are extremely air and moisture sensitive. These compounds thus are prepared, handled and reacted in the exclusion of air, and it takes a lot of technical know-how in dealing with these compounds, and that is one of the reasons why organometallic chemistry has thus far stayed confined to very few chemists practicing in this area. In the beginning of the course, what I had thought is that I would give you a brief overview of the history of organometallic compounds. I believe this is very important as to give you a perspective as to how these compounds evolved over time with discoveries made along centuries. This would also give you a view as to which compounds were discovered first and which came next, and obviously it would be important to stress that the easier ones got discovered earlier and the more challenging and rigorous ones are coming of late only when we have number of technical know-how about handling them. So, in this first week we will give you a brief history of organometallic compounds, and then we move to various classifications of organometallic compounds, and then from there we would dwell on the stability and reactivity of metal carbon bonds. The reference book for this course is three of them. One is Estenbroek, Organometallics, 3rd edition, Robert Crabtree, The Organometallic Chemistry of Transition Metals, and B.D. Gupta and A.J. Elias, Basic Organometallic Chemistry. These books as well as any other books on the subject will do. Now, to give you a feel for how important this field is, I would say that 9 Nobel Prizes have been awarded to the area of organometallic chemistry. That starts with 1908 Ilstrich for organoarsenic compounds, followed by Grignard and Sabatier for Grignard reagent in 1912, Ziegler-Natta in 1963 for Ziegler-Natta catalyst that has led the world in polymerization, Fisher and Wilkinson in 1973 for sandwich compounds, Brown in 1979 hydroboration reaction, Hoffman and Fukui in 1981 for Woodward-Hoffman rule, Novels, Nayeri and Sharpless in 2001 for asymmetric hydrogenation, Chauvin, Strock and Grubbs in 2005 for alkene metathesis, and lastly Heck, Negishi and Suzuki in 2010 for palladium catalyzed cross coupling reactions. So, these give you a feel for the significance of this field, which is only about 100 or 200 years old, but it has made tremendous impact in our society. And also the diversity in the area tells you about the depth and the breadth of the fields which organometallic chemistry possess. To start back at the history, the first organometallic compound dates back to 1760 when the first organometallic compound in form of dimethyl arsine oxide was prepared. This compound dimethyl arsine oxide is called cacodyl oxide because it has a very bad smell. It was prepared by Charles Louis Cadet working in a military pharmacy in Paris in an attempt to make invisible ink for military use. So, this is the first reported organometallic compound that one can trace back to. Subsequent to this, about in 1827, the first olefin complex called Zeiss's salt having the formula sodium Cl3 Pt C2H4 was prepared. Now, this complex is not a very simple complex, because this complex has a binding of gaseous ethylene molecule onto a platinum. So, one important attribute of organometallic chemistry is the ligand metal interaction. The metals interacts with ligands in various ways, and this is a representative compounds which has led to development of lot of theory in how a gas or olefin in a form of a gaseous atom binds to a metal like platinum. Subsequent to this, in 1840, R. W. Bunsen synthesized dialkyl diarsane R2AS AsR2. Then in 49, E. Franklin, a student of Bunsen, synthesized alkyl zinc. This was done from the reaction of ethyl iodide with zinc, giving diethyl zinc, ethyl zinc iodide and zinc iodide. Now, if you recall that this reaction is somewhat similar to a oxidative addition reaction, where alkyl halide adds to a zero valent metal center. Now, probably the first or among the first few methods that were used to synthesize organometallic compound starts with this oxidative addition reaction. And what we see later on, that in many catalytic processes oxidative addition reaction becomes an important step, and hence we see the origin of this step lies in synthesis of some of very important compound at very early stages of the history. Now, in 1852, E. Franklin synthesized alkyl mercury halides. Again, we see the similar kind of oxidative addition reaction occurring here between methyl iodide and mercury, giving methyl mercury iodide. So, this seems to be a time when lot of new organometallic compounds were being synthesized. In 1852, C. J. Lowig and E. Schweitzer prepares lead alkyls. Again, following the similar method of oxidative addition, whereby ethyl iodide was added to sodium lead alloy, giving tetraalkyl lead. 1859, W. Wallach and A. Sarafik generates aluminum alkyl iodides, again following the same method of oxidative addition happening between alkyl halide and metallic aluminum, giving dialkyl aluminum iodide and alkyl aluminum diiodide. 1863 saw the famous Friedel, C. Friedel and C. M. Kraft prepare organosilane compounds by the reaction of silane tetrachloride with dialkyl zinc, giving alkyl silane chloride and zinc dichloride. Now, this we see is a different reaction than that of the oxidative reactions that we have been seeing so far. This reaction is sort of a transmetallation reactions, where zinc alkyl migrates onto silicon and zinc itself abstracts the chlorine and becomes a zinc chloride. 1866, J. W. Wanklin prepared halide free magnesium alkyls, and this was done by reaction of diethyl mercury with magnesium, giving diethyl magnesium and mercury. This reactions opens up a new role for alkyl mercury as a transmetallation reagent. And thus far, not only on this, alkyl mercuries have been used for transmetallation reactions in preparing transition metal organometallic compounds in many other instances. 1868 saw M. P. Stuttenberger prepare the first metal carbonyl complex in the form of COPtCl2 dimer. Here, a gaseous carbon monoxide molecule binds to platinum. I must say that organometallic compounds offer a great opportunity to study variety of interaction occurring between metal and the ligands. The ligands are of varying types, and metal also has different electronic configurations and different orbitals like s, p, d and f, which interact with the metal with the ligand. In 1890, Elmond prepares the first binary metal carbonyl compound in form of nickel tetracarbonyl. This compound is very toxic and has to be handled with care. This discovery led to the formation of a big chemical company which came to be later known as ICI. In 1909, W. J. Pope prepared the first sigma transition metal complex in form of trimethyl platinum iodide. See, one of the definition of organometallic compound lies in the fact that they contain metal carbon bonds. Now, the metal carbon bonds can be several type. It can be a sigma bond as well as pi bond, and there are a lot of examples which were synthesized that had a sigma bond or pi type interaction of the ligand with metal. So, from this instance, this is the first sigma organotransition metal which was formed on platinum. In 1917, W. Schlenk prepares alkyl lithium. The reaction used was transmetallation reactions using mercury alkyls. So, lithium with dialkyl mercury give lithium alkyl and mercury, and ethyl lithium with dimethyl mercury gives methyl lithium and diethyl mercury. This is a ligand exchange reaction. Now, methyl lithiums are extremely difficult compounds to handle as they are pyrophoric. They, when exposed to air, they instantaneously start burning. But these compounds are extremely good compounds as alkylating reagents, and they play a crucial role in organic synthesis. In 1927, A. Job and A. Casal prepares chromium carbonyls. So, in 1931, W. Haber prepares the first transition metal hydride complex in form of CO4 FeH2. 1938 saw O-Rowland's hydroformylation reaction that produced aldehydes from ethylene, carbon monoxide and hydrogen gas. Thus, the reaction of ethylene with CO and H2 gives aldehyde. This was a very important reaction and went on to be a big hit in industry, producing tons of aldehyde by using this method, and this is came to be known as hydroformylation reaction. Various catalysts, organometallic catalysts, particularly rhodium and cobalt, discovered for this transformation. In 1943, E. G. Rocco reported the first direct synthesis that initiated large scale production and use of silicones. The reaction used was methyl chloride with elemental silicon, copper catalyst as 300 degrees centigrade, giving dimethyl silyl dichloride and other isomers. Silicon was also a commodity which was produced large scale in industry. Beginning from 1951, probably what one can say is the golden age of organometallic chemistry started, with many new and interesting compounds being synthesized at this period. In 1951, M. J. S. Dewar proposes the theory of alkene binding to transition metal complexes. These are really very engaging theory, as it involves the interaction of ligand orbital with that of the metal ones. In 1953, J. Chatt and L. A. Dunkinson elaborated the theory and came up with Dewar-Chatt-Dunkinson theory. This theory explained how the bonding happened in Zeise's salt that was discovered in 1827, about 100 years later. This was a very fascinating discovery at that time, because it was found that during the alkene metal interaction, there are actually two interactions which are happening. One, a sigma interaction that happened from the metal p orbital, the olefin p orbital onto a empty metal d type orbital, and the second interaction which is called a pi interaction that happened between the filled metal d orbital onto a vacant pi star orbital of the olefinic ligand. And these two interactions occurred in a symbiotic fashion. If the first one reinstated the second one, which reinstated the first one. As a result, this metal olefin interaction became very strong. These had a great implication in chemical industry as well as in chemical catalysis, as these metal olefins are important intermediates in various catalytic reactions. In 1951, P. Pawson and S. A. Miller prepared the first sandwich complex in the form of ferrocene, which is dicyclopentadienyl iron. Prior to that, it was extremely difficult to believe how would two cyclopentadienyl ligands attach to a metal center. Ferrocene is a very stable molecule where we have two cyclopentadienyl ligands attaching to a metal center, and the overall stability of this complex arises from the 18 valence electron of this metal center, which leads to a very stable form of this compound. In 1952, H. Gilman prepared organocuprates in the form of lithium copper dimethyl. These are very good alkylating reagents and have an extremely important role in organic synthesis. Another important discovery was made in the following year in 1953. Wittig prepared the olefin from phosphonium ylides and carbonyl compounds. Actually, the reaction of aldehyde with phosphonium ylides led to these various olefins, the cis and the trans olefins. This was a very important discovery, as one could make olefins from carbonyl compounds. Impact of this discovery was recognized by the fact the Nobel Prize for 1979 was awarded to this reaction. 1955 saw another important discovery in terms of olefin polymerization with a report from Carl Ziegler and Giulio Natta. What Carl Ziegler and Giulio Natta did was they could see that olefins in terms of ethylene, propylene or other higher order olefins in presence of triethyl aluminum and titanium chloride could give very long chain polymers, and that was a significant discovery that within 10 years time was awarded a Nobel Prize. And we have seen that polymers have transformed the world significantly. Actually, in the beginning of the century, there was a belief that long chain polymers are probably very difficult, challenging, or probably never be formed because of entropy factor going against the formation of polymerization. However, it was later realized that the enthalpy gain due to the formation of the polymers through monomers overcomes the loss of entropy and results in overall formation of the polymers. In 1956 saw another Nobel Prize awarding discovery by H. C. Brown when he discovered hydroboration reaction. So, hydroboration reaction became a very important reagent method for carrying out HB addition in unsaturated compounds. A lot of boro reagents were discovered subsequently, and finally the reaction was recognized by a Nobel Prize in 1979. In 1964, E. O. Fisher prepared the first carbene complex in form of CO5WCOMe methyl. This is the compound where there is a double bond between tungsten and the carbon center. This was the first ever multiply bonded metal carbon compound. These are usually known as carbene. Subsequently, in 1965, G. Wilkinson and R. S. Coffey reported the first homogeneous olefin hydrogenation catalyst in the form of triphenylphosphine rhodium chloride. This is a very active catalyst for carrying out hydrogenation reactions of olefin under homogeneous conditions. 1973, E. F. Fisher prepared the first carbene complex in ICO4CrCr. So, in that way Fisher was instrumental not only in making metal carbon double bond, but also in making metal carbon triple bond, and this led to his receiving Nobel Prize in 1973. As I said that beyond 1950 onwards, the golden age of organometallic chemistry probably unfolded. These compounds are extremely important and very exciting, and they carry out very important transformations in various catalytic cycles. In 1981, G. Baker reported the first C-P triple bond in terms of butyl C triple bond P. 1982, R. G. Bergman reported first CH activation. CH activation is an important area of research because if activated and functionalized, they can be very useful in producing various compounds having different functional group. But the difficulty in activating CH lies in their ubiquitousness and very strong carbon hydrogen bond. So, CH activation is a topical area of research in present time, and this had been initiated by Robert Bergman's first report of CH activation about 30 years back in 1982. In 1995, G. Cubus reported the first sigma complex of a silane, where a metal is bound to a silicon hydrogen bond through a sigma complex. Now, these are very challenging compounds, because this sigma complex may undergo oxidative addition to give metal hydride and metal trimethylsilyl moiety. In 1997, Keith Cummins reported carbon as the ultimate ligand, when carbon moiety was solely bonded to molybdenum. What we saw is that this discovery of organometallic compounds started with compounds which are very stable, easy to handle, and then gradually as the technique and behavior improved, it went on to become something which is very difficult and very sensitive ones. Even they too were isolated over time. The field expanded over about 200 years or so, from somewhere where it was practically non-existent to somewhere where it is becoming an important part in various chemical catalytic reactions. Also, what we saw is that oxidative addition was previously probably the first reaction that came in play in synthesizing this organometallic compound. Later on, reactions like ligand metathesis, transmetallations reactions were also brought in to synthesize various organometallic compounds. Another important aspect which evolved over the years was in the understanding of organometallic compounds, particularly the understanding of the metal ligand interaction. One started appreciating by looking at these compounds that these metal ligand interactions are of varying types, and they changed with the nature of the ligands. So, there were ligands which are just sigma bonded, there were ligands which are sigma and pi bonded, and all of these had different kind of binding ability and attributes. So, what it throws open is that a huge area with a very diverse type of bonding and very diverse kind of compounds with properties that emerged as the field unfolded. Also, it became clear that with time, as one was able to handle the exclusion of air and synthesis of these compounds under such conditions, the more and more important compounds came into form. So, with this I will sort of summarize today's lecture, which was on historical perspective of organometallic compounds. We saw what kind of methods were used over time to prepare some of the very important compounds like Grignard reagents, Wittig reactions, hydroformylations, hydrogenations, that as well as sigma complex, as well as Zeise's salt, which went on to become very important markers in the field of organometallic chemistry. With this, I would summarize this lecture, and we will move on to the next lecture, which will cover the bond polarity and the reactivity of various organometallic compounds. Thank you.